In this video, we're going to be looking at topic 3A, energetics, and this is part of the IGCSE chemistry course, and we're going to be focusing on the double content from Edexcel. So we're going to be looking at exothermic and endothermic reaction. We'll be describing simple calorimetry experiments for neutralisation, dissolving, displacement and combustion reactions, how we can calculate the heat energy change using Q is equal to Cm delta T. We'll then be able to calculate the molar enthalpy change, which is delta H, and then looking at the practical aspects of these reactions as well. So if we start off by looking at what is an exothermic reaction, you will have learned this back in Key Stage 3. So when we get a reaction that gives out heat to the surroundings and causes a temperature rise, we call this an exothermic reaction. So in these reactions, the products have got less energy than the reactants because the reactants are releasing energy in the form of heat. And we get this rise in temperature when the heat is released to the surroundings. So examples of exothermic reaction would be combustion, otherwise known as burning reactions, and this is probably the most common example. But we also have when we take a metal and we put it in an acid, a neutralisation reaction or a displacement reaction should give us an exothermic result. Now the opposite of these is endothermic, and this is when a substance takes in heat from the surroundings and we get a temperature decrease, and that's our endothermic reaction. So here we're getting the temperature going down, so we should see it getting colder, and in this case the products of the reaction have more energy than the reactants because they are absorbing heat from the surroundings, so we get this decrease in temperature. And some examples are thermal decomposition, chemical cold packs, dissolving ammonium chloride in water and some other salts dissolving in water is endothermic, and photosynthesis as well. Now we can talk about the change in energy in terms of something called the enthalpy change, and it is given this unit here, which is delta H. So the triangle is the Greek letter delta, and it just means change. And the H is the term that we use for enthalpy. So this is delta H is meaning the amount of heat energy that is taken in or given out in a reaction. And it is calculated simply by looking at the difference in energy between the products and the energy of the reactants. And we're going to look at an equation that we can use to help us figure this out. If our delta H value has a negative sign in front of it, then it tells us our reactant is exothermic. So we are seeing our temperature rising. If our delta H value is positive, then our reaction is endothermic. So we see our temperature decreasing. So we can help figure out which sign is going to go in front of the delta H value by simply looking at what happens to the temperature. Now we need to understand a very specific value that relates to our water, and this is known as specific heat capacity. Now you may cover this in physics in more detail, but we just simply have to know the specific heat capacity as it relates to water and water only. So specific heat capacity of a substance is how much energy is needed to raise the temperature of 1 gram by 1 degree Celsius. So we're linking heat energy, mass, and temperature. So we have our units as joules per gram per degree. So joules is our energy, grams is our mass, and our degrees Celsius is our temperature. And the specific heat capacity of water is 4.18, or sometimes they may ask you to use 4.2, and that's joules per gram per degrees Celsius. That means in order to increase the temperature of 1 gram of water by 1 degree, I need to put in 4.18 joules of energy. And this value is going to be used in every calculation that you do for the energetics topic. So we can calculate the amount of heat energy, or Q, by looking at the mass and the temperature change, because the amount of heat energy is directly proportional to these values. So we can use this equation down here at the bottom, where Q is equal to mc delta T. So remember we said specific heat capacity was linking energy, mass and temperature, so we put all of these together in an equation. So we have the heat energy, which is Q, the mass, which is M, and this is always the mass of water or the mass of the solution, and that will be important later on, as you'll see. And then specific heat capacity is given the term C, and temperature change is this delta T. Remember, delta being the capital letter in Greek that tells us change. Now, using this heat energy that is being gained or lost in any reaction, we can measure that using our calorimetry experiments. And that allows us to say, for a specific amount of mass that is being used, we make this particular heat energy. But we know from topic 1E, the calculations topic, that we always compare things using the mole. Because the mole is this unit that allows us to compare different atoms or elements to each other, because remember, every element is going to have a different mass. So we standardize them all using this substance, the mole. So we do the same thing in energetics. If I want to compare the amount of energy that's been giving out when I burn ethanol and compare that to when I burn another alcohol called propanol, if I burn different amounts, so if I burn 1 gram of ethanol versus 0.5 grams of propanol, I cannot compare those two values. So I have to convert it into this thing called the molar enthalpy change. And it puts the units into kilojoules per mole, and then that allows us to compare our values. So the molar enthalpy change is this definition at the bottom, and it is the amount of energy that is either gained or released, depending on if it's exo or endo, when 1 mole of a substance undergoes a reaction. So we're always relating it to 1 mole so that we can then compare them. So let's look at some of these calorimetry experiments. We're going to start off by looking at the enthalpy of combustion. This is the most common experiment that you will see in exam questions. It does come up quite often. It tends to be combustion and neutralisation are the two that are most common, but you do need to know all 4. So in this experiment, we use something called a spirit burner in order to burn an alcohol. And a spirit burner is a safe way that we can burn alcohol, because remember, as you know from common sense, alcohols are very flammable. So we can't just simply take the alcohol and set it on fire or put a Bunsen flame near it. What we do is we use this thing called a spirit burner, and it is essentially a glass jar that we can see down at the bottom here, and it has a rope inside it. And the rope is immersed into the alcohol, and then it comes up through the lid at the top, and we light the rope on fire. And what we're actually doing is we are burning the alcohol that is being absorbed by that rope. So we're not burning the rope itself, we're just burning the alcohol that's on it. Now, because this is going to be a flame, we cannot simply just stick a thermometer in it and see what the temperature is, because it's going to be masked by the flame. So what we do to figure out the heat energy that's being released is we use it to heat water in a copper can surrounded by insulation. So the copper can is used because it is a good conductor. Copper is a very good conductor of heat, and the insulation is there to trap the heat in the water. So we would probably use some sort of lid or insulating card, and we would use something called a draft shield, and this is our insulation here. And it just means that once the heat is transferred from the alcohol to the water through the copper can, it's kept in there. So what we do is we heat the water and we get a reasonable temperature change, maybe about anywhere between 20 to 40 degrees Celsius. It doesn't really matter as long as you know your start and end temperature, and you can then calculate the values for Q and delta H. And I'm going to show you how we do that. And this at the bottom here is the equation that we get. So we have the ethanol reacting with oxygen when it's being combusted to make carbon dioxide and water, and we call this complete combustion. So we make sure that we have enough oxygen here so that all of the ethanol burns. So we would get a table of results that looks a little bit like this. We have the volume of water that we use, typically is 100 or 200 centimetres cubed. We have the mass of the burner and the ethanol before the experiment, and the mass of the burner and ethanol after the experiment, the starting temperature and the end temperature. So let's look at how we then put that into our Q is equal to Cm delta T value first. Now, when we're looking at the volume of water, we have it in centimetres cubed, but the density of water is 1 gram per centimetre cubed. And what that means is that 1 centimetre cubed of water weighs 1 gram. So whatever value you have in centimetres cubed, that is the same value in grams. So our mass of the water is 100. Please note that this M, as we've said, has to be the mass of water. This is not the mass of the ethanol. We'll come to that in just a minute. C is always 4.18, and my delta T here is just simply going to be 62.8, take away 21.5, which gives me a value of 41.3. That's my temperature change. So I substitute all of that into my equation, and I get 4.18 times 100 times 41.3, and I get a value of 17260 joules. And then to turn that into kilojoules, I divide by 1,000. So your Q value will always be in joules, and then you convert it into kilojoules. But that is just the heat energy being released. We want to calculate the molar enthalpy. So remember, our molar enthalpy value is this delta H. And what we need to do is we need to calculate this by taking the heat energy and dividing it by the number of moles of ethanol that we burned. So that's what this middle calculation is. This is the moles of ethanol that have been burned. So we figured out how much ethanol was burned, and we do that using these two values here. So if I subtract 136.58 from 137.36, I figure out that I have burned 0.78 grams of ethanol. I can then divide that by the molar mass, which is 46, and it gives me a value of 0.01696 moles. Okay, so remember you learned this back in Unit 1E, where we have our moles, mass, and MR triangle. So you learned that back in topic 1E. So now I have Q as 17.26. Now I have N as 0.01696, and I substitute it into my answer here. So I do 17.26 divided by my number of moles, and I get an answer of 1,020 kilojoules per mole, and the negative sign tells us that the reaction is exothermic, and we know this because we have a temperature rise. Now, a typical value for the combustion of ethanol is 1,370 kilojoules per mole. Now, just to remind you, our answer was 1,020. So our answer is a little bit lower than what it should be. Now, the reason for this is we have possible sources of error, and this is a very, very common exam question, so I would strongly recommend that you learn these sources of error because they do come up quite a bit. Now, the main sources of error is that we lose some heat to the surroundings due to the lack of insulation. Whilst we can put a lid and put a draft shield, we can't confirm that all of the heat from the fire or all the heat from the alcohol burning is going to go into the water. So heat loss is a very common issue. We can also have incomplete combustion where we don't have enough oxygen. Okay, so this is when we have a lack of oxygen. And we can see that this happens because we get a buildup of soot on the copper can. So on the bottom of the copper can, you start to see this black soot building up, and that tells us that we have incomplete combustion. So we're not actually giving out all of the heat energy that we possibly can. A way that we can reduce these is we can use some setup called a bomb calorimeter. And basically all this is it's encased in some sort of plastic cover, and it essentially allows the substance to be burned in pure oxygen, so we're guaranteeing complete combustion, and because it's in a closed system, we guarantee that we have no heat loss. So if we were going to do this professionally or in a lab, like in industry, we would use a bomb calorimeter for this. Now, the second practical is the enthalpy of displacement practical, and you learned about displacement back in topic 2D, which was the reactivity series. So remember, displacement is when a more reactive metal takes the place of a less reactive metal. So we have to know our reactivity series to make sure that we're going to get an actual reaction here. But in this case, we are being told that we have zinc reacting with copper sulfate. So zinc is higher on the reactivity series than copper, so it should displace it. And what we do is we have our solution of copper sulfate, we add in the metal powder, and we stir the two things together. And as we stir it, we watch the thermometer and we look for the maximum temperature that is recorded. So this is an exothermic reaction. So we're looking for a temperature rise and we watch to see the maximum. And again, we can calculate Q and delta H. So our equation is we have zinc metal and copper sulfate. We get this displacement reaction where the zinc takes the place of the copper and we make zinc sulfate and copper metal. Now we do the calculation in this term exactly the same way. So we first figure out our Q, or our heat energy, by using our volume of water, our specific heat capacity, and our temperature change. So our volume of water is 50, and remember that is then going to weigh 50 grams. We use the mass of zinc later, so let's skip past that. Our delta T is going to be 27.3 take away 17, which is a temperature change of 10.3. So I substitute this in to find my heat energy value of Q. So Q is 4.18 times 50 times 10.3, which is 2,152.7 joules. And then I divide by 1,000 and I get my answer in kilojoules. But again, that's my heat energy for using 1.2 grams of zinc. I always want to convert it to my molar enthalpy. So in order to do that, I have to calculate the number of moles of zinc that are used. So my mass of zinc is 1.2, my MR is 65, so I get a number of moles of 0.0185, and then I substitute in my delta H to my delta H equation, Q divided by N, so 2.1527 divided by 0.0185, and I get an answer of 215 kilojoules per mole. And again, we have a negative sign to show that it is exothermic because we have a temperature rise. Notice that I did everything the same in terms of the in terms of the calculation. The only thing that is changing is my values. Moving on to the enthalpy of solution, this is set up very similar to the enthalpy of displacement. All we're doing is just changing out the substances. So instead of using a salt and an aqueous solution of a salt and a metal, this time we're using a solid salt and we're dissolving it in water. So we weigh out a specific mass of the salt and then we dissolve it in the water. And this time we're going to be looking for a minimum temperature. So this is an endothermic reaction. And it may only be a couple of degrees that it goes down by, but that's okay, as long as we see a slight change. So in this case, we're going to be dissolving ammonium chloride into water to make an ammonium chloride solution. But again, we can calculate Q and delta H. So to calculate Q, we take our specific heat capacity. Our volume of water is 100 centimeters cubed, so that's 100 grams. And our delta T is going to be 18.3 take away 5.1, which gives us a value of 3.2. I multiply all of them together and I get a Q value of 1.3376 kilojoules. I calculate my number of moles of the ammonium chloride that was dissolved. and that is the mass divided by the MR. So I dissolved 5.2, so we've recorded that here, we have our known mass, divided by 53.5, which is my MR, and I get this value of 0.0972, and I calculate my delta H using my Q divided by N, so 1.3376 divided by 0.0972, and I get a value of 13.8 kilojoules per mole. Notice the difference this time. We have a positive sign in front of our delta H value because this is endothermic. We see a temperature decrease. Nothing has changed in my calculation. The only thing that is different is I'm just using different values. The last one that you need to know is an enthalpy of neutralisation. Now you may set it up looking like the picture here, or you may use a titration setup, which you've probably been discussing in topic 2F, which was the acids and alkalis. And if you are a triple student, you will have carried out a titration, but don't worry too much about the actual setup. It will be more what you do with the values. So in this case, it is the reaction between an acid and an alkali to form a salt and water. Now, this one is slightly different in terms of how we actually carry out the calculation. And the reason for that is we cannot easily work out our temperature change. We have to figure out our temperature change using a graph. Once we get that temperature change, then the calculation is the same. So it's just this first bit before it that's a little bit different. And this is a very, very common exam question. And this could be worth 5 to 6 marks because they'll ask you to draw a graph and then do a calculation. So in this case, we're reacting sodium hydroxide plus hydrochloric acid to give us sodium chloride and water. Now, the reaction itself is an exothermic reaction. So what we should see is we should see our temperature increasing. Now, what we actually see is we do see the temperature going up, but then eventually the temperature is going to decrease. And the reason for that is we are adding excess acid. In other words, we are adding more acid than we need in order to neutralize the alkali. So what we do is we add the excess acid. Once we get the neutralization, that's going to be at our maximum temperature. Once the neutralization is complete, then all we are doing is we are adding cold acid to the alkali, and that then accounts for the alkali decreasing, for the temperature of the alkali decreasing. So we have an increase in our temperature until we get to our neutralization point, and then we get a decrease. So when we plot this graph, what we do is we draw 2 lines of best fit. So I have my volume of acid along my x-axis and my temperature along my y-axis. I draw 2 lines of best fit. So this one showing the increase, this one showing the decrease. And where these 2 lines cross over, so at this point here, that is going to be the volume of acid that I need in order to neutralize, and it is also going to show the maximum temperature. So from the crossover of the lines, I get my max temperature and the volume of acid that is used. And these are the 2 things that I need in order to do my calculation. So now what I have is my volume of acid I've read from the graph. So this 28 comes from the graph. My volume of alkali I had set at the beginning, in this case was 25. So my total volume of mixture is 53 centimetres cubed, and that's going to be 53 grams. I know my concentration, and I know my mole ratio, and then I can work out my delta T as well. So delta T is going to be equal to 12.5, because it's 31.8 to take away 19.3. So I can work out my heat energy, which is Q. So I have 4.18 times 53 grams times 12.5, and I get an answer of 2.7693 kilojoules. Now, this particular calculation is a triple calculation, working out the number of moles. So what you may find in an exam is they will tell you this. If it's in a triple paper, you are expected to carry out this calculation. But if you are a double student, do not worry, you will most likely be given this value. But in order to work out the number of moles, we figured out the concentration of the alkali, which you're told in the question, and you multiply it by the volume that is used. And I work out that I have 0.05 moles. As I said, for a double paper, they would tell you the number of moles used was 0.05. I can then use this in my delta H equation, so Q divided by N, and I get a value of 55.4 kilojoules per mole. Notice that we have this temperature rise. So again, this is an exothermic reaction, so I put a negative sign in front of my value. Now, the last thing that we need to discuss is just some assumptions that we make in these enthalpy calculations, because sometimes this can come up as a question. As you've noticed, we did the same calculation every single time. And in every single one of them, we assumed that the density of the solution is 1 gram per centimetre cubed. We assume that the density of any solution that we use is always the same of water. Now, we can make this assumption because the solutions that we use are mostly made up of water. If you have a copper sulfate solution, or CuSO4, you'll know that the state symbol is aqueous. That means we've taken some copper sulfate and we've dissolved it in water. So the majority of that solution is actually made up of water. So we always assume that whatever the volume is, that is going to be equal to the mass. So 100 centimetres cubed is always 100 grams. We also make the assumption that the specific heat capacity is always the same as water. So we always use a value of 4.8 or 4.2. The question will specify which one they want you to use, but we never use any value other than this. And we also assume that the mass of the solid that we add to the water is so small that it is negligible. So adding any mass of zinc or any mass of any metal, for example, for a displacement, is not going to change what mass of water that we're going to use. So we always simply use whatever the volume was, that's the mass. So let's finish up by looking at a past paper question here. So this is a question that is looking at the temperature change when lithium iodide dissolves in water. So this is the enthalpy of solution. Okay, but it doesn't matter which enthalpy it is, we are going to carry it out in exactly the same way as we have for any others. So the student measures the steady temperature of the water before adding the lithium iodide. He then adds the lithium iodide, stirs it, and then records the maximum temperature that is reached. So in this case, because we're saying it's a maximum temperature, hopefully we can figure out that this is going to be an exothermic reaction. So we're given our thermometers and we want to then read off the values and figure out what our temperatures was. So if we look at the temperature after, that's going to be the second one. So we can see that it is going to be a value of 22.3 because each of these lines is going to be a value of 1. And each of the lines in the middle is therefore 0.2, and because it's in the centre, it's going to be 22.3. Before adding the lithium iodide, it's the same scale that we're working off of, so we can see that we're going to get a value of 16.7. Please make sure that you do read these carefully and you do have it to 1 decimal place. You cannot go any closer than 1 decimal place because of the accuracy of the thermometers. And then the temperature change is simply 22.3, take away 16.7, and it gives you a value of 5.6. Now in a second experiment, using the same mass of water, so let's just go back. Our mass of water is 100. we use 100 grams. The student records a temperature increase of 4.9. So notice in this case, it's not relying on you having the correct answer from part A. From part B is giving you a new temperature to use, so you don't need to worry about any transferred errors. So we want to use the expression to calculate the heat energy. They're telling us they want us to use 4.2. So my heat energy is going to be 100 times 4.2 times the temperature change, which is 4.9, and that gives me an answer of 2058 joules. Okay, notice that they do want the answer in joules here, they do not want it in kilojoules. And there's your 2 marks. So in the experiment, 6.3 grams of lithium iodide was used. We want to calculate the number of moles. So we're going to use our mass, moles, MR triangle. So to work out my number of moles, it is the mass divided by the MR. So the mass is 6.3. I'm told the MR is 134, and that gives me an answer of 0.047 moles. 2 marks again. In part C, a third experiment, the student obtains these results. Notice that they are similar to the last set, but again, this is to ensure you don't have any transferred errors, so you're not relying on getting part B correct to get part C. So if you can't quite remember how to do the number of moles, you're not being penalised here for that same thing. So we want to calculate the molar enthalpy change. So delta H is going to be equal to Q over N. So Q is 2,400, N is 0.048, and that gives me a value of 50 kilojoules per mole. And in this case, we're not told if it is exothermic or endothermic, so we can simply ignore the sign. But remember, if it was exo, you would have a negative sign, and if it was endo, you would have a positive sign. It is best practice to always put those in. If this was a 3-mark question, you would be getting 1 mark for the sign. Typically, if it's a 2-marker, they're not going to be asking for that, but it's good practice to always put in a sign where you can. So in this case, our answer is 50 kilojoules per mole. And there you can see the answers to the past paper questions. And that's everything for topic 3A energetics for the double content. Hopefully everything has made sense, but if there's anything that you're not sure about, please feel free to leave a comment below, and we hope to see you back soon.